Physics is an approximation. Every theory we have, every equation we write, every prediction we make, all of it is approximate. Not approximately true in the sense that it's almost right but might be slightly off. Approximate in a more fundamental sense. Our theories are simplified descriptions of reality, valid only in certain regimes, breaking down when pushed too far. This might sound defeatist, like I'm saying physics doesn't really work, but that's not what I mean at all. I'm saying something more subtle and more profound. Physics works incredibly well within its domains of validity, but those domains are always limited. Every theory is an approximation to a deeper theory, which is itself an approximation to something even deeper. Let me tell you why this is true, what it means, and why I think it's actually beautiful. When I was learning physics as a young student, I thought we were discovering the true laws of nature. Newton's laws, Maxwell's equations, thermodynamics. These were the rules the universe followed. We were uncovering reality, revealing the mathematical structure underneath physical phenomena. And in a sense, that's true. These theories work. They make predictions that match observations to incredible precision, but they're not the final truth. They're approximations, valid in certain limits, breaking down outside those limits. Take Newton's laws. For centuries, we thought these were the fundamental laws of motion. Every object continues in uniform motion unless acted on by a force. Force equals mass times acceleration. Action equals reaction. These laws seemed universal, applying to everything from falling apples to orbiting planets. And they do work remarkably well. We use Newton's laws to send people to the moon. We use them every day in engineering, in architecture, in technology. They're not wrong in any practical sense, but they're approximate. Einstein showed us with special relativity that Newton's laws break down at high velocities. When things move close to the speed of light, Newton's predictions diverge from reality. Time dilation, length contraction, relativistic mass, none of these appear in Newton's theory. Newton's laws are an approximation valid when velocities are much smaller than the speed of light. In that regime, they're excellent. Push beyond that regime, and they fail. Then Einstein showed us, with general relativity, that even in the low-velocity regime, Newton's laws are approximate. In strong gravitational fields, space and time curve. Gravity is not a force, it's the curvature of space-time. Newton's inverse square law is an approximation to Einstein's field equations. Again, in weak gravitational fields, Newton's approximation is excellent. The GPS satellites in your phone need general relativistic corrections, but for throwing a ball, Newton is fine. But it's still an approximation, and even general relativity is an approximation. It's a classical theory ignoring quantum effects. At very small scales, at very high energies, quantum mechanics becomes important. And we don't have a complete theory of quantum gravity yet. General relativity breaks down at the Planck scale, at black hole singularities, at the Big Bang. General relativity, our best theory of gravity, is itself an approximation to some deeper quantum theory we haven't fully discovered yet. Every theory in physics follows this pattern. Maxwell's equations for electromagnetism are brilliant, incredibly successful, but they're classical, approximate. The true theory is quantum electrodynamics, which includes photons, virtual particles, quantum fluctuations, and even quantum electrodynamics is approximate. It ignores the weak and strong nuclear forces. The full theory is the standard model of particle physics, unifying electromagnetism with the weak force, including the strong force. And even the standard model is approximate. It doesn't include gravity. It has parameters we have to measure rather than derive. It's effective, not fundamental. There's something deeper, string theory maybe, or something we haven't thought of yet. Physics is approximations all the way down. Or rather, approximations all the way up, each level valid in certain regimes, emergent from deeper levels. Let me tell you why this is inevitable. It comes from something called effective field theory, one of the most important ideas in modern physics. The basic insight is this. At any given energy scale, you can only probe physics at that scale and above. Physics at much smaller scales, much higher energies, is effectively invisible. It contributes to what you observe, but in a way that can be summarized by a few parameters. For example, at everyday energies, you don't see quarks and gluons, you see protons and neutrons, which are made of quarks and gluons, but you don't need to know about quarks to describe a proton's behavior at low energies. You just need a few parameters. The proton's mass, charge, spin, all the complicated internal structure of the proton, all the quantum chromodynamics describing how quarks interact, all of that is hidden. It's integrated out, summarized in effective parameters. This is effective field theory. At each energy scale, you have an effective theory that describes physics at that scale, with parameters that encode the effects of higher energy physics you can't directly see. As you go to higher energies, you need better theories, more accurate descriptions. The effective theory breaks down. You have to include new degrees of freedom, new particles, new interactions. But the lower energy theory doesn't become wrong. It remains valid in its regime. It's an approximation, but a good one. And it's simpler than the high energy theory, easier to work with, perfectly adequate for calculations at low energies. Physics is approximate because we're always working with effective theories, valid at certain scales, derived from deeper theories at higher scales. And here's the thing. We don't know where this tower of effective theories ends. Maybe there's a fundamental theory at the bottom, a theory of everything from which all else emerges. String theory aspires to be this. Or maybe it's effective theories all the way down. No bottom, just deeper and deeper levels we haven't probed yet. We don't know. And in practice, it doesn't matter for most purposes. Each effective theory works in its domain. That's enough. Let me give you another example. Thermodynamics. The laws of thermodynamics are incredibly powerful, incredibly general. Energy is conserved, entropy increases, temperature flows from hot to cold. These laws apply to everything from steam engines to black holes. But thermodynamics is approximate. It's a statistical theory describing average behavior of systems with many particles. At the microscopic level, statistical mechanics is the deeper theory. Individual molecules don't obey the second law. They undergo reversible time-symmetric dynamics. Entropy increase emerges statistically from the fact that there are overwhelmingly more high-entropy configurations than low-entropy ones. It's a statistical tendency, not a fundamental law. And statistical mechanics itself is approximate. It assumes classical particles, or sometimes quantum particles, but treating them with certain approximations. The full quantum mechanical description is more complex. Thermodynamics works brilliantly for macroscopic systems, but it's an emergent, approximate theory, not fundamental. And that's okay. It's still incredibly useful. Now let me tell you about quantum mechanics itself. You might think quantum mechanics is fundamental, the deepest theory we have, and it might be for certain aspects of reality. But even quantum mechanics, as we usually formulate it, is approximate. Standard quantum mechanics treats time as a classical parameter, not a quantum variable. It assumes a fixed space-time background. It doesn't include gravity. These are approximations valid when gravitational effects are negligible. In quantum gravity, time itself might be emergent, might not exist at the fundamental level. Space-time might be emergent from quantum entanglement. Everything we think is fundamental in quantum mechanics might itself be approximate, and the measurement postulates in quantum mechanics, the rules about wave function collapse, these are almost certainly approximate. They're effective descriptions of decoherence, of entanglement with the environment, not fundamental processes. A more fundamental theory, maybe the many worlds interpretation, maybe something else, would derive measurement as an emergent phenomenon. The measurement postulates are approximations to deeper quantum mechanical behavior. Even our most fundamental theory is approximate in various ways. Let me connect this to something I've worked on extensively, the holographic principle. The holographic principle says that physics in a volume of space can be described by a theory on the boundary of that volume. The interior physics is emergent from the boundary. This means that our usual description of physics in three-dimensional space is approximate. It's an emergent, holographic description, valid in certain limits but not fundamental. The fundamental theory is on the boundary in one fewer dimension. Our 3D physics is a holographic projection, an approximation that works well at low energies and large scales, but breaks down at the Planck scale or near black hole horizons. Add S, CFT makes this precise for certain spacetimes. The boundary theory is exact, fundamental. The bulk theory, the physics in the interior, is approximate, emergent, derived. Our entire framework of three-dimensional space with particles and fields moving around in it is an approximation. The fundamental reality is different, lower dimensional, more abstract. Physics is approximate because even the dimensionality of space is approximate, emergent from a more fundamental description. Now let me tell you about perturbation theory and why it reveals the approximate nature of physics. In quantum field theory, we calculate things using perturbation theory. We start with free particles, no interactions, which we can solve exactly. Then we add interactions as small corrections, perturbations. We calculate effects to first order in the interaction strength, then second order, then third order, summing up an infinite series. Each term is a correction to the previous approximation. This works incredibly well. Quantum electrodynamics predictions agree with experiments to 10 decimal places or more. It's the most precisely tested theory in physics. But here's the thing. The infinite series doesn't converge. If you keep adding terms, the series diverges. At some order, adding more terms makes the prediction worse, not better. This is because perturbation theory is an asymptotic expansion, not a convergent series. It's an approximation that gets better for a while, then breaks down. There's a limit to how accurate it can be. And this is true for all our quantum field theories. We can't calculate exact answers. We can only calculate approximate answers using perturbation theory, accurate to some finite precision but not perfect. Physics is approximate because our calculational methods are inherently approximate, giving us asymptotic series rather than exact solutions. Let me tell you about renormalization and how it shows physics is approximate. In quantum field theory, when you calculate loop diagrams, contributions from virtual particles, you get infinities. The integrals diverge. To deal with this, we use renormalization. We introduce a cutoff, a maximum energy scale where we stop integrating. This gives finite answers. Then we absorb the cutoff-dependent terms into redefinitions of parameters like mass and charge. The physical predictions don't depend on the cutoff in the limit where the cutoff goes to infinity, but the cutoff represents the scale where our theory breaks down, where new physics comes in. Renormalization works because our theories are effective theories, valid only up to some cutoff energy. Beyond that, new degrees of freedom appear, new physics takes over. The infinities are telling us that our theory is incomplete, approximate. By renormalizing, we're saying we don't know the physics at very high energies, so we'll parametrize our ignorance with a few measured quantities like masses and charges. Our theory is approximate, but the approximation is well controlled. Physics is approximate because renormalization shows our theories break down at high energies, requiring cutoffs and effective descriptions. Now let me address something subtle, measurement precision. Even if we had perfect theories, perfect equations describing fundamental reality, our measurements are approximate. Every measurement has finite precision. You can't measure a position or momentum or energy to infinite precision. Quantum mechanics itself limits precision through the uncertainty principle. And practical limitations, instrument sensitivity, noise, make measurements even less precise. So even if the theory is exact, our comparison with experiment is approximate. We calculate predictions to some precision, measure results to some precision, and check if they agree within error bars. This means physics is necessarily approximate in practice, limited by measurement precision, even if the underlying theory were exact. But more deeply, measurement might be fundamentally approximate. If quantum mechanics is correct, observables don't have definite values until measured. And measurement is an interaction, an entanglement between system and apparatus. Different measurements give different results. Incompatible observables like position and momentum can't be simultaneously measured. The very act of measurement is approximate, capturing only partial information about the quantum state. Physics is approximate because measurement itself is approximate, providing limited information about quantum systems. Let me tell you about chaos and why it makes physics approximate. Many systems are chaotic, sensitive to initial conditions. A tiny change in the starting state leads to exponentially growing differences in the evolution. Weather is chaotic. You can't predict it accurately more than a few days out, no matter how good your theory or how powerful your computers. Small uncertainties in initial conditions amplify exponentially. This means that even with perfect equations, perfect theories, we can only make approximate predictions for chaotic systems. The approximations in our measurements of initial conditions lead to inevitable inaccuracy in long-term predictions. And it's worse than that. Quantum mechanics introduces fundamental uncertainty in initial conditions. You can't know both position and momentum precisely. This quantum uncertainty feeds into classical chaos, limiting prediction even more fundamentally. Physics is approximate because chaos amplifies uncertainties, making long-term predictions impossible even with perfect theories. Now let me connect this to cosmology. We have a standard model of cosmology, lambda CDM, describing the universe's evolution. It works very well, matching observations of the cosmic microwave background, galaxy distributions, supernovae, but it's approximate. It assumes the universe is homogeneous and isotropic, the same everywhere on large scales. This is only approximately true. There are galaxies, clusters, voids, structure at all scales. We treat structure as small perturbations on a smooth background. This perturbation theory works well for small perturbations, but it's approximate. In dense regions like galaxy clusters, the perturbations are large and the approximation breaks down. We have to use numerical simulations, which are themselves approximations. We can't simulate every particle in the universe. We coarse-grain, approximate, use effective descriptions. And the cosmological model has dark matter and dark energy components we don't understand. We parameterize them, describe their effects, but we don't have fundamental theories of what they are. The model is phenomenological, approximate. Physics is approximate because cosmology requires treating structure as perturbations and using components we don't fundamentally understand. Let me tell you about computational limits and how they make physics approximate. Even if we had perfect theories and perfect measurements, we couldn't solve the equations exactly for complex systems. Three bodies interacting gravitationally can't be solved analytically. You need approximations or numerical methods. Add more bodies, and it gets worse. A galaxy with billions of stars? Impossible to solve exactly. Quantum mechanics is even worse. The Hilbert space grows exponentially with the number of particles. A system of just 300 qubits has more quantum states than there are atoms in the observable universe. You can't write down the wave function, let alone compute its evolution. We have to approximate. Mean field theories, perturbation expansions, numerical simulations with finite precision, all approximations. We can never compute exactly what perfect theories predict for complex systems. Physics is approximate because computational complexity makes exact solutions impossible for all but the simplest systems. Now let me address something philosophical. Are the approximations converging toward a final truth, or is it approximations all the way down? The reductionist dream is that there's a fundamental theory, a theory of everything, exact and complete. All our current theories are approximations to this fundamental theory. As we probe higher energies, we discover deeper layers, getting closer to the final truth. String theory fits this dream. It claims to be the fundamental theory from which everything else emerges. All our effective theories are approximations to string theory at lower energies. But maybe that's wrong. Maybe there's no final theory. Maybe it's effective theories all the way down, each valid in its regime, each approximating deeper theories we haven't discovered yet in an infinite tower. This is more unsettling, but possibly more realistic. We've never found a final theory in any domain. Every time we thought we had one, we discovered it was approximate, emergent from something deeper. Maybe that pattern continues forever. Maybe physics is fundamentally approximate, not because we're failing to find the truth, but because truth itself is stratified into levels, each approximating the next. Physics might be approximate not as a temporary limitation, but as a permanent feature of reality. Let me tell you why I find this beautiful rather than depressing. Approximations are incredibly powerful. They let us understand complex systems by focusing on what matters, ignoring irrelevant details. You don't need quantum field theory to design a bridge. Newtonian mechanics is enough, simpler, easier to work with. The approximation is appropriate for the problem. Different approximations are useful in different contexts. For GPS satellites, you need general relativity. For planetary orbits, Newtonian gravity is fine. For atomic physics, quantum mechanics. For chemistry, molecular orbital theory. Each level of approximation is optimized for its domain. Using a more fundamental theory would be overkill, unnecessarily complex, obscuring the relevant physics. Physics is approximate, but that's a feature, not a bug. Approximations are tools, and different tools are appropriate for different jobs. And approximations reveal structure. The fact that thermodynamics emerges from statistical mechanics tells us something profound about how macroscopic laws arise from microscopic ones. The approximation is revealing the mechanism of emergence. The fact that general relativity approximates to Newtonian gravity in the weak field limit shows us how Einstein's radical reconceptualization connects to familiar physics. The approximation is a guide to understanding. Approximations are not failures of understanding. They're stages in understanding, each level illuminating different aspects of reality. Let me connect this to how physics actually progresses. We don't discover complete theories fully formed. We start with approximations, simple models capturing essential features while ignoring complications. Then we refine the approximations, add corrections, account for effects we initially neglected, gradually build up more accurate descriptions. Sometimes we discover the approximation breaks down completely, and we need a revolutionary new framework. Relativity replacing Newtonian mechanics, quantum mechanics replacing classical mechanics. But even then, the old theory remains valid as an approximation. Newton's laws still work at low velocities. Classical mechanics still describes macroscopic objects. Progress in physics is not discarding wrong theories and replacing them with right ones. It's understanding the domains of validity of approximate theories and discovering deeper theories that encompass and explain the approximations. Physics is approximate, and that's how we make progress, by refining approximations and discovering their limits. Now let me address what this means for the goal of physics. If everything is approximate, what are we trying to achieve? We're not trying to discover the final exact truth. We're trying to understand how nature works at different scales, how different descriptions relate to each other, how complex phenomena emerge from simpler ones. We're building a web of theories, each approximate, each valid in its domain, each connected to others through limiting procedures and emergence. The standard model of particle physics, general relativity, thermodynamics, fluid dynamics, chemistry, biology. Each is approximate, each emerges from deeper levels, each is valid in its regime. Understanding these connections, how macroscopic emerges from microscopic, how classical emerges from quantum, how effective theories emerge from fundamental ones, that's the goal. Not a single theory of everything, but a framework of interlocking approximate theories, each explaining its domain and connecting to others. Physics is approximate, and the goal is understanding the structure of approximations, not eliminating them. Let me tell you about a practical example, climate science. Climate models are physics-based, using fluid dynamics, thermodynamics, radiation transfer, all well-established theories. But they're approximate. We can't simulate every water molecule, every photon. We coarse grain, use grid cells kilometers across, average over smaller scales, and we parametrize processes we can't resolve. Cloud formation, turbulence, ocean eddies, these happen at scales smaller than our grid. We use approximate formulas tuned to observations. The models work reasonably well, capturing major climate features, making useful predictions, but they're approximate, with uncertainties, with systematic biases. This doesn't mean they're useless. It means we need to understand their limitations, quantify uncertainties, improve approximations where possible. Climate science is physics, and like all physics, it's approximate. But approximate doesn't mean unreliable. It means having limited precision and known domains of validity. Now, let me connect this to black hole physics and the information paradox. For decades, we thought black holes destroyed information, violating quantum mechanics. This seemed like a fundamental conflict between general relativity and quantum theory. But I believe the resolution is that both theories are approximate. General relativity is approximate, breaking down at black hole singularities. Quantum field theory in curved space-time is approximate, ignoring back reaction and quantum gravity effects. When you use approximate theories beyond their domains of validity, you get paradoxes. The information paradox arises from pushing approximate theories too far. The resolution requires quantum gravity, a deeper theory that encompasses both general relativity and quantum mechanics as approximations. String theory, holography, these are steps toward such a theory. Physics is approximate, and paradoxes often arise from using approximations outside their domains of validity. Let me tell you about symmetries and how they relate to approximations. Many of our best theories are based on symmetries. Special relativity from Lorentz symmetry, general relativity from diffeomorphism invariance, the standard model from gauge symmetries, but these symmetries are often approximate too. Lorentz symmetry might be violated at the Planck scale. Gauge symmetries might be emergent rather than fundamental. Diffeomorphism invariance might not hold in a discrete theory of quantum gravity. Symmetries are guides, powerful organizing principles, but they might be features of effective theories rather than fundamental reality. And symmetry breaking is central to physics. The Higgs mechanism breaks electroweak symmetry, chiral symmetry breaking in QCD, phase transitions breaking symmetries. Symmetries hold approximately in some regimes and are broken in others. They're not absolute features of reality, but approximate regime-dependent principles. Physics is approximate, and even its fundamental symmetries might be approximate, emergent, regime-dependent. Now let me address the role of mathematics. Physics uses mathematics, but mathematical models are approximations to physical reality. A perfect sphere, a point particle, a frictionless surface, these are mathematical idealizations. Real objects are never perfect spheres, never point-like, never frictionless. The mathematics is exact, but its application to reality is approximate. We idealize, simplify, ignore complications to make problems tractable. And sometimes the mathematics suggests things that aren't physical. Negative probabilities in some formulations of quantum mechanics, unphysical gauge degrees of freedom, mathematical singularities that probably don't correspond to physical singularities. We have to interpret the mathematics, distinguish physical from unphysical, understand which mathematical features represent reality and which are artifacts of our description. Physics is approximate because mathematical models are idealizations, and we have to interpret them carefully to extract physical predictions. Let me tell you what this means for the philosophy of science. Naive scientific realism says our theories describe reality as it truly is. If a theory predicts electrons, electrons are real. But if physics is approximate, this is too simple. Electrons are real in the sense that electron theory is a good approximation in certain regimes, but electrons as point particles are not fundamental. They're excitations of quantum fields, which themselves might be emergent from something deeper. Realism needs to be sophisticated, recognizing that theories describe reality approximately at certain scales from certain perspectives. What's real at one level might be emergent at another. And anti-realism, the view that theories are just instruments for predictions without describing reality, is too extreme. Our theories do describe reality, just approximately, at different levels. A better view is structural realism. The mathematical structure of our theories captures real structure in nature, even if the ontology, the stuff our theories talk about, is approximate and scale-dependent. Physics is approximate, and this requires a nuanced philosophy of science, recognizing layers of approximation and emergence. Now, let me bring this all together. Why is physics approximate? Because reality is complex, stratified into levels, each level emergent from deeper ones. Because we can only probe finite energy scales, only measure with finite precision, only compute with finite resources. Because theories are tools optimized for particular domains, not universal descriptions. Because emergence creates new effective descriptions at each scale. Because chaos and complexity limit predictability. Because measurement is limited by quantum mechanics. Physics is approximate fundamentally, not just practically. And that's okay. That's how science works. We build better approximations, understand their limits, discover deeper theories, which are themselves approximations to something deeper still. The tower of effective theories, each approximate, each valid in its regime, each emerging from and connecting to others. That's the structure of physical knowledge. And it's beautiful. It means reality is richer than any single theory can capture. It means there's always more to discover, deeper levels to probe, better approximations to develop. Physics is approximate. And recognizing this, embracing it, understanding it, that's essential for doing physics well and for appreciating the incredible success of our approximate theories at describing the approximate nature of this beautifully complex universe.